I am Carl Ross of the University of Portsmouth in the United Kingdom. The oceans. 3/4 of the Earth's surface is covered by water. The Earth's surface is covered by water is over 10 times larger than the surface area of the Moon. The greatest depth of the ocean is found in the Mariana Trench. This is 11.52 kilometers deep or 7.16 miles deep. Ocean resources. Methane deposits in the form of frozen hydrates have been found at depths of 2 miles and more, or 4.83 kilometers and more. Off the coast of the USA, 30 gas fields have been found. In one gas field alone, it is believed that there is sufficient gas to satisfy the USA's needs for 105 years, based on the 1996 consumption rate. Ocean resources. The quantity of this methane is about twice the amount of all fossil fuels on land and shallow waters. That means it's twice the amount of the fossil fuels such as oil, gas and coal on land and shallow waters. If this methane is divided equally amongst all mankind, then each and every one of us will get a chunk of methane of a mass of about 1,670 tons. Public transport versus private transport. Public transport is not much good except in cities. In rural areas and suburban areas, it's not terribly good. Try taking 10 bags of garden refuse to the rubbish tip by public transport. Try taking your old and infirm relative to the hospital by public transport. Try doing your weekly shopping at the out-of-town shopping mall by public transport. Methane resources. The total value of this deep-sea methane is about 536 times the GDP of the USA. Some eminent people say we should leave this methane where it is. However, I believe that if the West plays on a level playing field and leaves the methane where it is, I doubt that the rest of the world will follow suit. Methane is too valuable to be left alone. Get used to it. We're going to burn it. Methane resources. This deep-sea methane, frozen methane, was discovered by Dickens and all and others. Dickens is from Rice University, Texas, in the USA. The USA and Japan are vigorously searching in the deep seas for this frozen methane, but not Europe. There's a map of the world, and you can see methane production. The deep-sea methane has been produced by the action of archaea under high water pressures. Archaea are similar to, but not the same as, bacteria. They're a group of prokaryotic single-cell microorganisms. Some of the methane is produced by the archaea through microbial metagenesis, while some of it is produced by thermogenic metagenesis, by the cracking of organic compounds. This is archaea. Looks similar to bacteria, but it's different bacteria. Archaea halobacteria. Costs of producing electricity per megawatt hour. Coal, 30 pounds. Gas, 38 pounds. Nuclear power, 39 pounds. Wind, 85 pounds per megawatt hour. Now here we have water, ice and methane hydrate joined together. This is burning methane hydrate. The methane hydrate is, and there you see burning methane hydrate. Looks like ordinary water ice. And here we have a diagram showing pressure temperature relationship for methane hydrate. Underwater methane deposits. Many eminent scientists believe that the temperature of the oceans has increased by about 0.5 to 1 degree Celsius since 1960. If global warming continues, the seas will continue to warm up. This may cause the plankton to die, with disastrous consequences for marine life. If the temperature of the seas gets sufficiently high, the frozen methane can evaporate and catch alight. The Bermuda Triangle. Many eminent scientists believe that the unexplained loss of ships and aircraft in the Bermuda Triangle were caused by the escape of methane gas. In the case of ships, if they become entrained in a large bubble of methane gas, they can completely lose their buoyancy and sink to the ocean's bottom without warning. Similarly, if a low-flying aircraft becomes entrained in a bubble of methane gas, it can explode without warning. Underwater methane deposits. Thus, it will be necessary to use the underwater methane to prevent it from catching alight. The methane can be collected by drilling a hole into the reservoir containing methane gas and sucking the gas out from under the methane hydrate. This will cause the pressure to fall in the area where it is frozen and cause the frozen methane to vaporize from this compartment to the reservoir immediately below. It must be remembered that the freezing and the boiling point of liquids are not only dependent on temperature, but also the pressure that the liquid is subjected to. If the pressure of the fluid goes up, the boiling and freezing points also go up, vice versa if the pressure goes down. This is why we cannot get a good cup of tea at the top of Mount Everest, because the atmospheric pressure at the top of Mount Everest is only about 0.34 bar, which is a third of atmospheric pressure, and because of this, the water boils at 70 degrees C. So you can't make the water hot in liquid foam, and that's why you can't get a good cup of tea at the top of Mount Everest. There you see a diagram of the Blake Ridge, which is off the east coast. And here we are in the Earth's atmosphere. We live in the atmosphere. About 90% of the mass of the atmosphere is contained in the troposphere, which is warming up and where the weather occurs. Less than 9% of the mass of the atmosphere occurs in the stratosphere, where aircraft fly. The ozone layer lies here. This absorbs the harmful rays of the sun. CFC gases damage the ozone layer. About 21% of the Earth's atmosphere is oxygen, about 78% nitrogen, 0.93% argon. These are not greenhouse gases. In fact, the greenhouse gases represent less than 1% of the Earth's atmosphere. Water vapor is a greenhouse gas. It is the third most abundant gas in the atmosphere, but as its lifespan is only a few days, mankind need not worry about it too much. CO2 is the worst offender of the greenhouse gases. Its concentration is 0.038%. It is the fifth most abundant gas. Over the last 300 years, its percentage has increased by about 35%. The problem with CO2 is that its lifespan is hundreds of years. That's the problem with it. Whereas water vapor is only a few days. The greenhouse gases are carbon dioxide, methane, nitrous oxide, ozone, which is O3, and water vapor. The present level of greenhouse gases allow the Earth to be inhabited by man. Without them, the Earth's average temperature would be about minus 90 degrees C. In other words, if we had no greenhouse gases, we couldn't live on planet Earth. Instead, the current average is a very pleasant 15 degrees C.
And this is what Keeling produced. His measurements started in 1958 at 315 parts per million carbon dioxide in the atmosphere. And the first thing that you notice is a rise and fall each year, which is the seasonal variation in carbon dioxide. Even in these early years, you could spot a rising trend, but you only get a true picture of the power of this graph when you stand back and track the changes through the decades, such that here, today, 2008, we're at 386 parts per million. This relentless year-on-year rise in carbon dioxide is the one undisputed piece of evidence in the whole global warming debate.
It meant that nobody could seriously argue with one simple statement. The human race has steadily increased the amount of carbon dioxide in the air. The significance of Keeling's discovery is simple, because carbon dioxide is a remarkable gas.
I can show you how carbon dioxide affects Earth's climate using this heat-sensitive or infrared camera, which is purring away here, and a candle, this glass tube, which is hooked up to this rather large canister of carbon dioxide gas. Now, if I light the candle, you'll see that on the monitor, the camera picks up the flame perfectly. Look at that. The hottest parts are glowing white. Now watch what happens when I turn on the carbon dioxide.
Just keep your eye on the flame.
The gas is invisible, so you don't see it fill in the tube. But as it comes in, you should see the candle start to disappear. There it goes. Look at that. What's happening is that the carbon dioxide in the tube is effectively trapping the heat.
The candle's warmth no longer reaches the camera. Instead, it's absorbed by the carbon dioxide inside the tube. That's exactly how carbon dioxide works in the atmosphere. It traps heat, preventing it from escaping into space, and warms the atmosphere in the process. The more carbon dioxide there
An experiment. The atmosphere. Do not worry, there is enough oxygen in the atmosphere to burn this deep sea methane, the mass of oxygen being about 100 times the mass of deep sea methane. The mean mass of the atmosphere is about 5.148 times 10 to the 15 tons. The Earth's mass of carbon dioxide is 1.956 times 10 to the 12 tons. If we burn this methane, it will release about 2.76 times 10 to the 13 tons of carbon dioxide into the atmosphere. So we might as well get used to it and do something about carbon dioxide footprint per person per year. It's about 20 tons per person per annum in the USA, about 18 tons per person per annum in Australia, about 11 tons per person per annum in the UK, about 6 tons per person per annum in Switzerland and Sweden, about 3 tons per person per annum in China, about 1 to 2 tons per person per annum in India, 0.1 tons per person per annum in Ethiopia, and only 0.01 tons per person per annum. Thus, it can be seen from the previous slide that for Africa to get into the 21st century, it will need to burn fossil fuels. If mankind burns 2 tons of methane per person per annum and uses alternative forms of energy, then mankind should have enough fossil fuels to last us for 1,000 years. Additionally, as a source of energy, fossil emergent countries' entry into the 21st century. Sir Winston Churchill once famously said, "Do not pull the tail of the Chinese dragon or you will awaken it." The Chinese dragon was awake but flapping its wings. Soon it will be in full flight. When this happens, 1 billion or so Chinese people will want private motorized transport. China is building one coal-fired power station every 4 days. The Indian tiger will follow suit. Energy used by India. Currently, India's middle class is 50 million strong, and India has about 61 million cars on the road. Economists believe that by the year 2030, India's middle class will swell to 543 million, and India will have 613 million. This is the Indian car that will change the world. It's called the Tata Nano. It's a people's car. It can. The Tata Nano, people's car, looks quite attractive. Its capacity is 623 cc's, 33 horsepower. Its maximum speed is 65 miles per hour with a town consumption of 50 miles per gallon. It is a 4 to 5 seater and its monocoque chassis is made from recycled beer cans. It meets EU requirements. Its current retail price is £1,200. This is another car that could do it. The Chinese-German car costs about £400 or about $600. It's made from carbon fibers, which are 10 times stronger than steel, and which it's designed by Volkswagen and built by China. It meets EU requirements. Looks what it can seat 2 people who sit in tandem, rather like sitting on a motorbike behind each other. It can do 258 miles per gallon and speeds up to 74.6 miles per hour. The chemical breakdown of methane. Methane consists of 1 part carbon and 4 parts hydrogen. Methane is CH4. If scientists can break down methane to carbon and hydrogen, the hydrogen can be burnt without causing a carbon footprint or by using a fuel cell. Using hydrogen to power automobiles, ships and aircraft can prevent the environmental problems mentioned in the previous slides. CO2 emissions. Combustion of methane will release about 27,600 billion tons of carbon dioxide. This figure is 110,000 tons greater than Britain's proposed maximum annual emissions. If this CO2 is released into the atmosphere, it will increase the CO2 in the atmosphere by about 1,511%. The scientists and the technologists will have to address this problem. For example, this is a possibility. It's a very extreme example, I admit, but nearby cities can be linked by road tunnels or tubes so that the CO2 can be trapped and scrubbed or injected into the ocean's bottom. The Channel Tunnel is 32 miles long. It costs $12 billion. It's very expensive because of the incredible feat of engineering. A conventional motorway costs about £28 million a mile. The tube motorway may cost twice a conventional motorway, which is £56 million a mile. Tunnels and tubes will have the advantage that they're weatherproof, so snow won't bother us. No gardening, no grit laying will be required. Motorway noise will be less of a problem. If the motorway is going past the city, that will be less of a problem. The green and pleasant land above the tunnel can be returned to nature. Similarly, the CO2 from factory chimneys can be scrubbed and injected. Now this is a drawing I made, it's just an idea. There's a tube there, you can see it's above the ground, it has 4 levels, the bottom level is emergency transport, southbound at the 2nd level, northbound at the 3rd level, emergency on the top. It's just an idea, and that's not a tunnel, that's a tube. There you can see another view of the tunnel, the tube, I beg your pardon, a road tube. It's supported above the land. If it goes through a mountain, then it has to have a tunnel there. That's basically a tube. This is a conventional highway modified to an enclosed double-decker. Now, double-decker motorways exist in the USA and also in Mexico. This is an enclosed double-decker. The bottom highway will be made of concrete, reinforced concrete. The highway above should be made out of a composite, because composites are 50 times stronger than concrete in compression, and they're light. The longest tunnel is the Japanese Seikan Railway Tunnel. It is 53.85 kilometers or 33.5 miles long. The longest road tunnel is the Norwegian Lærdal Tunnel. It is 24.5 kilometers or 15.2 miles long. The above tunnels have water and mountains respectively above them. My tube motorway is in the air above it. One method of removing the carbon dioxide is through the use of suitable chemicals. For example, if carbon dioxide is mixed with soda lime, it changes to 2 harmless substances, namely chalk and water. Other chemicals that can neutralize carbon dioxide are potassium superoxide and lithium hydroxide. There are many others available as well. The above chemicals are also... A German scientist called Klaus Lackner has invented a plastic which absorbs carbon dioxide. The absorbed carbon dioxide can be washed off the plastic by blowing it with water vapor, and it can be reused. So the carbon dioxide can be collected. Other chemicals yet to be invented can be used for the same purpose. These chemicals can be placed in the exhausts of automobiles where they can be replaced at suitable intervals. The chemicals can also be placed inside tube and tunnel highways and factory chimneys where they can absorb the unwanted carbon dioxide. The unwanted carbon dioxide can be buried in the deep oceans where they will freeze due to the high water pressures. I think it is better to bury the carbon dioxide in the deep oceans because 71% of the oceans naturally absorb about 50% of the carbon dioxide from the Earth's atmosphere. This causes the oceans to become more acidic, as the CO2 takes the form of carbonates, bicarbonates, and carbonic acid. If the oceans become too acidic, the plankton will die and cause havoc to marine life. However, it does have the advantage that CO2 can be collected from the oceans and nullified. Thus, perhaps nuclear-powered ships can collect the CO2, freeze it, and dump it overboard, as described later. Now, this is a method of injecting the CO2 at the ocean's bottom. This is a section of the Blake Ridge. The vertical axis, the depth, MBSF, stands immediately below seafloor. Soil at the top suggests frozen carbon dioxide in the middle, and we pump it down there. But the pressure of the water will cause it to freeze, and because its density is greater than the water, it will remain stable for
And buried, but this is a decade away. Critics say it's all far too slow.
Now here we have a table showing carbon dioxide hydrate formation at temperatures, pressures, and water depths. So you can see that at the bottom row, the temperature is 5 degrees C, the water depth is 252 meters, which is not very deep, and that will freeze there. If you go deeper, the better it is. Alternatively, frozen CO2, which is called dry ice, torpedoes, can be dumped overboard a ship which is sailing over deep waters. As the density of frozen CO2 is 1.56 more than that of water, the frozen CO2 will sink. When the frozen CO2 reaches the appropriate depth, it will remain frozen for many centuries because of the high pressure. Now here we have a picture of a ship throwing frozen CO2 overboard. It's not fired, but it could be catapulted, and because the frozen CO2 is 1.56 the density of the water, it will freeze. As it goes past much about 250 meters, it won't evaporate. I just show the diagram of the CO2 torpedoes sinking in the seabed. They should gain quite high speeds, sink in the seabed, where they will remain. I just show the diagram of combating climate change. You can see the ship there on the left, discharging the CO2 dry ice torpedoes. On the right, underneath that ship, is a submarine tanker, and down below is an underwater drilling rig, and the submarine tanker can collect the gaseous oil from the and this shows the pressure temperature equilibrium diagram for CO2. On the left, CO2 solid and gas, CO2 liquid and gas on the right, and CO2 gas at the bottom. The average depth of the ocean is a little less than 3 miles, about 5,000 meters. For large structures to dive to these great depths, they will need to be constructed from composites or similar materials. The strength-to-weight ratio of a composite can be more than 10 times larger than the strength of high steel. At the bottom of Mariana Trench, the pressure is about 1158 bar, that's 1158 atmospheres, about that, which is 16,800 pounds per square inch, which is roughly just under 8 tons per square inch. Now, a double-decker bus in London weighs about 8 tons. So on each square inch of your submarine, you've got the weight of a double-decker bus acting on it. It's a huge load. Currently, a large submarine can only dive to a depth of about 400 meters, which is 1,310 feet. The construction of a large submarine pressure hull for very large. If a submarine of internal diameter 10 meters, which is 32.81 feet, and constructed high tensile steel is required to dive to the bottom of the Mariana Trench, then its design wall thickness will have to be a minimum of 2.3 meters, which is 7.58 feet. That means it will have no reserve buoyancy and sink to the bottom of the ocean, and you can't get it up again because it has no reserve buoyancy. If such a vessel is constructed of a high-strength plastic composite, its design wall thickness will have to be a minimum of 0.91 meters or 2.98 feet. That is, it is buildable and has reserve buoyancy, unlike a similar vessel constructed in high tensile steel. That means this underwater drilling rig or the submarine has reserve buoyancy, so you'll need to have ballast tanks which will be filled so it sinks to the bottom, and when you want to get up again, you will vacate the ballast tank.
Minus 530. 530. Minus 436.
29 if you can make it front. Don't get too close to it.
Brilliant! That was, look at that. I think that it just reached.
This is the buckling of a railcar tank under an internal vacuum. The tank was initially filled with steam, the surplus steam escaping. It was then sealed off. When the steam cooled down, turned into water, the volume inside, the volume of water inside was much less than the volume of the steam, and it came under an internal vacuum and buckled like that. Now this thing is buckled with less than an atmospheric external pressure, because this is equivalent to a submarine under external pressure. The only manned submarine to conquer the Mariana Trench was August Piccard's Trieste. This was achieved on the 23rd of January 1960. The Trieste had a spherical pressure valve of 6 foot internal diameter, which is 1.83 meters, and about 6 inches thick, which is about 15.24 centimeters. It was constructed in high tensile steel. Thus, its internal diameter was about 6 feet, and its external diameter was about 7 feet. It had no reserve buoyancy, even though it was only a small vessel like that. It had no reserve buoyancy, and to help it float, its pressure hull was hung from a large 11-compartment float filled with petrol, which is called gas in the USA, as shown by the next slide. So there you see the Trieste. You can see the 11-compartment float on the top. The pressure hull down the bottom is spherical. It has 2 people. The gasoline tanks have openings at the bottom of the bases, so that underwater the water will come in, and it won't rise to the surface of the water because it's much more dense than gasoline, but it'll pressurize the gasoline tank so that the inside of the tank, the pressure is the same as the outside, and therefore they won't break at this great depth. Unlike the spherical hull, which has got water. And then the Trieste, you can see the float on the top, down the bottom, and then the Trieste at sea. And then the Trieste pressure hull, which is a spherical vessel at the bottom, with a plexiglass window, which is called perspex in Britain, but which its scientific name is polymethyl methacrylate. It's about 7 foot external diameter, and alongside you can see a man there about 6 foot diameter, showing the size of it. And there's Jacques Piccard and Lieutenant Donald Walsh of the US Navy inside the Trieste prior to making their record-breaking dive. They're the only people who have conquered the Mariana Trench, and as far as men conquering the Mariana Trench, there's less people doing that than have been done on walking on the surface of the moon. Jacques Piccard is... The next slide shows an underwater drilling rig designed by myself together with my former student Jeff Lafley-Lane in 1997. The material of construction of the rig was a high-strength plastic composite. The rig was designed to dive to a depth of about 5,000 meters or 3.11 miles with a total mass of 40,000 tons. The rig had plenty of reserve buoyancy. A depth of 5,000 meters will be deeper than 60% of the ocean's bottoms. And there you see a drawing of the underwater drilling rig. This can pump CO2 at one depth of 3,600 meters where it will freeze and sink. Or it could retrieve methane. So it has a double purpose to bury the CO2 and to retrieve the methane. And you can see it there. Now, if you think, and there's a drawing of the rig, the donut shape, which houses the personnel. The diameter of that toroid, the donut is called a toroid, is 80 meters diameter. The internal diameter of the tube is 10 meters. The whole thickness of the tube is 0.345 meters. It's made from a composite which has about 10 times the strength of high tensile steel. And then the layout of the rig, you can see the vertical pressure vessel houses a drilling derrick. The toroid, or the donut shape, houses a PWR nuclear reactor, which is necessary for this vessel to survive underwater. Japanese drilling. This is the Times, April the 14th, 2008, just over 2 years ago. Hidden source of power that could last 100 years. I think that's an underestimate of it. Now, the Japanese have managed to retrieve some of these frozen methane hydrates. The way they did it was to pump hot water down to the methane hydrates, where it's melted and vaporized and got it up. Conclusions. For Africa to get into the 21st century, it will need to burn more fossil fuels. At present, fossil fuels are the cheapest form of energy. Public transport is not much good, except in cities. It's not much good in suburbia, and not much good in rural areas. The impact of the 1,200-pound Indian car is likely to be enormous, and so too is the 400-pound Chinese-German car. They're likely to have enormous impact, and there'll be billions and billions of people driving motor cars. Other third world countries are likely to produce similar cheap cars. This type of vehicle will probably be powered by deep-sea methane, which is plentiful. Don't forget, there's 10,000 billion tons of it in the ocean bottoms. It is likely that in the future many submarine pressure hulls will be constructed in man-made materials such as glass, boron and carbon fibers, and also ceramic and metal matrix composite, and also carbon nanotubes. Carbon nanotubes have roughly 250 times the strength of high tensile steel. Submarines constructed in man-made fibers will lend themselves to be readily constructed in various forms. They've got to be constructed with materials which have high strength-to-weight ratio so that the submarine has positive buoyancy. Retrieval of deep-sea methane together with the sea barrier of carbon dioxide can be achieved with the aid of deep-diving submarine-type structures, or underwater drilling rigs. The role of the scientist and the technologist. The problem of environmental meltdown has to be addressed. According to Professor James Lovelock, within about a century, the temperature in the tropics will rise by about 5 degrees C, and the temperate regions will rise by about 8 degrees C. This will cause our green and pleasant land to turn desert. The effect of this will be about much of mankind. Sometime in the future, so don't worry about it at present. We are all right at the moment. Lovelock believes that mankind will survive by a few mating pairs who inhabit the Arctic and Antarctic circles. Thus, immediate remedial action is required to alleviate the predicted catastrophe, which will be of biblical proportions. Positive feedback. James Lovelock says that 60% of the Arctic ice cap melted last summer. This will cause positive feedback and worsen the melting of the ice because planet Earth will absorb more sunlight due to the darkening of the Arctic Ocean. So this is an idea I had, is using mirrors to shine back the sun. We can counteract this effect by placing mirrors on our roofs or elsewhere to cool the Earth down by shining the sun rays back into outer space. Additionally, we can paint our roofs and our roads with white paint to further cool planet Earth by allowing it to reflect more sunlight back into outer space. Buoyant white surfaces can also be floated in the oceans to reflect the sun's rays. We can cool the planet down. Now, the problem is that most of the sunshine is absorbed by the oceans, which are 71% of the surface, and they're dark. If we whiten the oceans, we can solve the problem. And one way is this. It might seem a bit extreme, but I think it's an idea. Alternative means of producing energy must also be used. If the scientists and the technologists are given the tools, they can finish the job. We can save the planet, but we must not waste time. We can have our cake and eat it too. We can use fossil fuels and not destroy ourselves. This is a book I wrote, Pressure Vessels, External Pressure Technology, which was used for designing submarine pressure hulls. It was published in 2001 by Howard Publishing of Chichester, but a new edition is coming out. It's Pressure Vessels, External Pressure Technology. The second edition has been published by Woodhead Publishers of Cambridge. So that should come out at the end of April 2011. It has design charts in it, which can be used for designing pressure hulls, which are not as conservative as PD 5500, which is the standard that's normally used in Britain. That is my URL, my homepage. And that's my email.